All right, what's going on, everyone? I am back with a problem in mechanics of materials dealing with axial deformation of a statically indeterminate or axial deformation problem that's statically indeterminate. And uh, um, and what we're going to do here is take a really popular problem. You have an axial member or some member, structural member that's fixed on both ends at A and C. You're given some material properties. Sometimes you're not. You don't. Sometimes you don't need those, but we're going to see that in a little bit. Okay, and it's fixed at two ends. You have a loading here, and what you have to do is try to find the reactions, the horizontal forces or the reactions at A and C here. And this time, what we're going to do is use the method of superposition. So sometimes you've probably done this by looking at, by just trying to come up with a compatibility relationship straight away. But here, we're going to use method of superposition, or what sometimes is called the force method of structural analysis. And usually in mechanics, this is like your first introduction. Anyways, what we're going to do here, I'm going to break this down real simple for you, is draw the reactions, identify the number of redundant forces and remove them, and then draw this loading and redundant diagram, what I call the loading and redundant diagram. I think they're used popular. That's a popular term. And then come up with what's the compatibility relationship this way, which is going to be the equation that we need in the statically indeterminate problem, and then solve. Okay. So here we've got again this structure here, A, B, C. Um, it's got loaded. It's loaded at 50 kips. Loaded at point B with 50 kips. It's an external load. Okay, it's an external load. It's not internal. It's external at that point B. All right, and then the total length of my structural member is 100 inches, and 25 inches is from the left is where point B is. All right, so the first thing I'm going to do is draw the reactions. Reactions here, I have AX and CX. Because I don't have any transverse loading, I don't need to worry about any kind of moment that would be here or a shear. Okay, and what we would do is find out that these would be going to zero anyway. And same thing with the other side. And really all that really matters is the horizontal reaction AX and CX. Okay, so we've drawn these reactions. And we have to figure out what is this redundant force, or how many redundant forces we have. Okay, so by looking at only this AX and CX here, and really only being able to look in the horizontal, the number of equilibrium equations I have here, the number of equilibrium equations I have to me are one. Okay, I only have one equilibrium equation, and that's sum of the forces in the horizontal, or in the X in this case. Okay, if we call X positive to the right. This is the only equilibrium equation I have. Okay, number of equilibrium equations. But the unknowns, okay, number of unknowns are two. Two unknowns. I have two unknowns, one equilibrium equation. This means I am statically indeterminate to the first degree. The first degree. Okay? So I have an insufficient number of equations. I need one more equation, and that other equation typically is called the compatibility equation. Okay? It's a relationship that kind of relates deformations. Now, in order for me to do this using the method of superposition, what I want to do is I want to say, what if how many forces do I have to remove to make this thing statically determinate? And that in this case, because I have only one equilibrium equation, I have to get it down to one unknown. So if I remove one reaction, let's say CX here, then it would be statically indeterminate. So what I can do by method of superposition is say, hey, let me say this whole thing right here is equal to, I'm going to draw it one time here, this right here by removing C sub x right here. I remove C sub x. So essentially I have what looks like a cantilever, right? But this with only axial loading, plus here this other structure, this exact same looking deal with with C sub x added on right here as a redundant. Okay, so here This at here, I just have to remember this would be, I have to make sure when I remove this, I just include my loading, which is 50 kips. That's a 50 kips here. And this is called my loading diagram. This is my loading and redundant diagrams. This is my loading diagram. This is my loading diagram. And this is my redundant diagram. This is my redundant. If I was statically indeterminate to the second degree, I'd have another redundant diagram, if you will. Redundant diagram here. Okay. Each of these two diagrams is statically determinate. And if I add these two up, what I'm saying is that, oh, this is going to be, it's going to result in my total structure with the two ends fixed and my 50 kip load. So this is what I've separated it. And it's nice because each of these is statically determinate, and I just have to analyze each one at a time, and I'll be able to, solve this problem. All right, so here I have here this is 25 inches, and this is 100 inches. And the thing I want to relate here is that, okay, I know that point C, in terms of deformation, point C should not move. So the total deformation at point C should equal 0. So I need to come up with a compatibility relationship for that. If I apply a 50 kip load here, I know that I'm going to have some deformation here, okay? And I will call this, with my loading diagram, I'm going to call this deformation delta C0. And then with this load right here, I'm going to have some deformation right here, and I'm going to call that delta C1. Okay, so my first redundant and my only redundant, but here, and so my compatibility relationship is that here I have delta C, which is equal to 0. I have no deformation at point C, is equal to delta C0 plus delta C1. Okay, delta C0 equals delta plus delta C1, which is great. Okay, one thing to note here is, one thing to make sure you stay consistent with is, if you draw your reactions here as going to the right, okay, AX and CX going to the right, you also want to make sure your redundant also goes to the right. You don't want to suddenly swap. All right, that's going to mess things up. You're going to get a negative sign that you don't need. It's just going to cause problems. And you're going to be like, why is my answer different than what it's supposed to be? All right, so here, you've got this right here. And each of these are pretty easy to solve for. So for instance, delta C0, the deformation here, it's the sum of the deformation in this region right here plus this region right here. If I make a cut here, the internal force here, let's see, blah, 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 I think NBC, I'll call this 0 equals 0. There's nothing here. And if I do a cut here and I look at the internal force in this region, I'll get NAB equals 50 kips in tension. So if you do a little free body diagram, you make that cut, you'll find that you have a 50 kip tension there. And then if I make a cut at any point here, I will find that NAC for the entire length, I'll call this NAC1, is equal to CX. And it's positive CX because it's in tension. Okay, this thing, the way that I've drawn this, okay, so this would be, these are all my internal forces going on. Delta C0 is equal to NAB LAB over EAAB, that cross-sectional area of AB, plus N BC LBC over EABC. So this is that summation for axial deformations. Okay, so you have to have some understanding of this already to have this video making sense. And this is 0 here. So obviously this whole term goes to 0, which is not unnecessary. And then here for delta C1, because I have only one internal force, no changes going on, no loading in between, I have here NAC1 LAC over EAAC, okay, which is, this is because NAC1 is CX, LAC over EAAC right here, okay? And now I plug these back into my compatibility relationship right here, so that I have delta C, which is equal to 0. The deformation of C is 0 at this reaction, or where I have this, right? And here I have NAB, LAB over EAAB plus CX LAC over EA AAC. Okay, right here. And thankfully EA, the cross section of this entire rod or this element is uniform. It's 3 inches squared, or you know what? We don't even need that number because it's equal to 0. And we multiply this whole thing through by EA and it's 0. Okay? And what we end up with is that CX is equal to minus NAB LAB over LAC, okay? And just make sure I did that right. Double check for me. Who knows? I could be wrong right here. And I know that NAB is equal to 50 kips in tension minus negative 50 kips, okay? Negative 50 kips times that LAB, which was 25 inches, divided by LAC, which is 100 inches, and that tells me that CX is equal to minus 12.5 kips. The negative tells me that CX is 12.5 kips pointing to the left. All right, CX is 12.5 kips pointing to the left right here. And now if I wanted to find AX, all I have to do is sum of the forces in the X equals 0. Go this way to the right. I would have AX plus, I'm just going to, I don't want to confuse things here. I'm just going to make my equilibrium equation look like this drawing right here, okay? I want my equation to reflect this drawing up here, right here. So I have essentially AX plus CX plus 50 kips equals 0. And then, because I know that it's negative 12.5, or opposite of that right here, I'm going to put this AX minus 12.5 kips plus 50 kips equals 0, and that tells me that AX equals negative 37.5 kips, which means it's 37.5 kips to the left. Okay, and those are my reactions. So that means I'd have to, if I want to draw this accurately, I'd have to, I'd either have to write this in as negative 37.5 kips with this arrow going that way, okay, minus 12.5 kips that way, or draw it with a positive number and the arrow pointing in the correct direction. All right, but those are minor details. The key is that when you choose, how do you know that this displacement is 0? You've chosen a reaction, right? You've chosen this reaction. So the reactions don't move unless there's something like ground settlement or something much more advanced going on that you're not really aware of. Okay, but these reaction points don't move for us in our mechanics problems, and so you can trust that deformation is 0. All right, so let me know if you have any questions. Hope this helps. Take it easy.